We begin by looking at a proton with a mass of about 1,800 electron masses sitting here, and an electron orbiting the proton. Now, electrons don't actually orbit protons in circular orbits. The position of an electron is given by a probability distribution, and this model is not reflective of what really happens in the atom. However, it is a very powerful model, and it gives us good predictions. Now, the electron orbits the proton. The proton has about 1,800 times the mass of the electron. These two particles actually orbit a common center of mass, but that center of mass is going to be about 1,800 times closer to the proton than it is to the electron. So we're just going to assume for now, without making a correction, that the orbit is about the proton. The charge of the electron we're going to designate by Q sub e. Charge of the proton, well, the electron will be negative Q sub e. The proton has equal and opposite charge, positive Q sub e. The charge of the electron, magnitude of QE, that is 1.6 times 10 to the negative 19th coulombs. Just a little bit of information here. The mass of the electron is as indicated, which is repeated here for some reason. Okay. If the electron orbits the proton at a distance of 10 to the negative 10th meters, and that unit, 10 to the negative 10th meters, we call an angstrom, and this distance is fairly consistent with the diameter, not the radius, of an atom. Okay, most atoms are pretty close to 10 to the negative 10th meters in diameter. Now, this goes for the heavy atoms as well as the light atoms, for reasons that we won't. Well, the heavy atoms hold their electrons closer, even though they have more electrons. And the outermost electrons are at about the same distance in a heavy atom as in a light atom. Your text will tell you more about that. If the electron is at this distance, just working through a numerical example before we get into the symbols, then the magnitude of the force between the proton and the electron is obtained by Coulomb's law. We just take K, Q1, Q2 over R squared. Since Q1 and Q2 are equal, the magnitude of the force will just be K, QE squared over R squared. And if we plug in QE, the charge of the electron, and R, the radius of this orbit, we see that the force is about 2.3 times 10 to the negative 8th newtons, on the order of a couple of 100 millionths of a newton. That doesn't seem like very much force, and on a lot of scales it isn't. But when that force acts on something with a mass of 9 times 10 to the negative 31st kilograms, we see that there's going to be an awful lot of acceleration. If we divide this by this, we get a huge acceleration, as we're going to see. Now, the acceleration of the electron will, of course, be always toward the proton, which is effectively toward the center of this circle, at least with the approximation that we're using. And that acceleration is going to be the centripetal acceleration that holds the electron in our hypothetical circular orbit. So that the centripetal acceleration is just going to be the magnitude of the force divided by the mass of the electron. And we calculate that very easily from the magnitude of the force and the mass of the electron. Here, of course, we do it symbolically, taking the kq squared over r squared divided by the mass of the electron, and we get this expression, which gives us the same thing that we would get if we divided this force that we just found by the 9.11 times 10 to the negative 31st kilograms here, and ends up being 2.5 times 10 to the 22nd meters per second squared. Now, that's a huge acceleration. Okay, that's the speed of light is on the order of 10 to the 8th meters per second, means we would attain the speed of light if we could maintain this acceleration for 10 to the negative 14th seconds. huge acceleration. The electron is really being accelerated toward the proton, and then as a result it has to go very fast around this circle in order to maintain its circular orbit. Okay, so we have this huge acceleration. Now, one thing that acceleration will do in classical electrodynamics, an accelerating charge emits electromagnetic radiation. And the greater the acceleration, the higher the wavelength, and the more energy is dissipated. At this acceleration, that electron is going to create some very high energy electromagnetic radiation and lose all of its kinetic energy and just fall into the nucleus here. And we know that that doesn't happen, so that leaves us in kind of a quandary. How can the electron go around the nucleus, the proton, at this kind of at the speeds that we get and with this kind of acceleration, and not lose all its energy almost instantaneously to the electromagnetic radiation that it creates? And we'll go a little further with this on the next clip.